second speaker of the morning session is Hatton from University. And we're going to talk about soft X-rays on Skyrmions.
Okay, thank you very much. As the chairman said, my name is Peter Hatton from Art and Physics at University, UK. And I'd like to thank the organisers for giving me the opportunity to come and give a talk to you. And also, and it may just be luck, that I'm following on from Don, who emphasised the use of soft X-rays for determining chirality, because what I'm going to try and do is sell you a technique. I'm going to try and explain that soft X-rays is really what you should be trying to use as a technique for understanding more about magnetic skyrmions. Okay, so we've seen pictures like this lots of times through the conference, because the two major techniques for imaging magnetic skyrmions are small angle neutron scattering, which gives you a diffraction pattern in reciprocal space. It gives you the wave vectors directly. It tells you about the spacing between the skyrmions in the skyrmion lattice. And then there's the real space equivalent from Lorentz transmission electron microscopy. And we've seen pictures like this all the time. These are the two premier techniques. And they both give you similar information about the size of skyrmions and the spacing of skyrmions. And of course, they're relying here on having well-ordered arrangements of skyrmions in B20 type materials, either bulk or thin film studies. And the principal technique for crystal structure determination, for determining the positions of atoms in lattices, is of course X-ray diffraction. And X-ray diffraction is used primarily for studying crystal structures. Again, it relies on having a well-ordered array, but has been used very rarely for studying skyrmions. And of course, the reason is that skyrmions are a magnetic texture, and X-rays don't have a magnetic moment. So neutrons have a magnetic moment and interact directly with the skyrmions. And again, with electron microscopy techniques, you can interact with the electron spin, whereas X-ray diffraction is primarily a technique that measures electron density rather than anything else. So, whilst it might tell you whilst electron microscopy might tell you about the crystal structure, it's not going to tell you about skyrmions, because it's not sensitive to the magnetism. Okay, now I'm part of a UK collaboration that's just started up, trying to look at skyrmions, particularly in the B20 and other bulk crystals, but also looking at thin films. And there are a number of us in the UK who are working collaboratively together. At Warwick, Geeta Balakrishnan is growing single crystal samples and powder samples. And Don Paul at Warwick is doing neutron elastic scattering, neutron small angle diffraction. At Cambridge, we've got access to Lorentz TDM and electron holography techniques with Paul Midgley. And at Oxford, Torsten Hedgedal has been doing thin film growth and hopes to move into patterning and architecture of thin films. And Torsten and I have also been collaborating together on X-ray diffraction techniques at the diamond signature. And then there's myself, this was pictured at Santa Fe Stevens, all the stuff like that. And Tom Lancaster, who does muon spectroscopy. And finally, we're helped by micromagnetic simulations by Hans Fangor at Southampton, and Andre Kavorka, who's doing theory of phase transitions and statistical physics and near field projects, etc. And we're all part of this Skyrmion project that was funded for a number of years. And what I want to do is try and give you an overview of what principally Thorsten Hedgedale and myself have been doing on soft X-ray diffraction and soft X-ray scattering. So, of course, to do that, we need samples, we need both single crystals and thin films, and then we've got access to all of these different techniques within the project. Okay, this is an outline of the talk. Firstly, what I'm going to try and do is explain to you how to make X-ray diffraction sensitive to magnetism, either directly by magnetic X-ray diffraction or by making use of resonantly enhancing the magnetic scattering. I'll try and go through the reasons that we use soft X-rays, and we take again account of resonant enhancement of the magnetic scattering that occurs close to absorption edges in the soft X-ray part of the spectrum. I'll then describe skyrmions in coproxyselenate, which of course as we've heard about both at this conference and elsewhere. And coproxyselenate is a unique compound in the B20 system. It still has the same space group as MNSI and FeGe, but of course its crystal structure is far more complicated than it's an insulator and multiferroic, so it has different transport properties. But within soft X-ray studies, coproxyselenate has a rather large role to play. I would guess that 90% of the soft X-ray studies that have been undertaken on that compound and that compound only. In fact, it's rare to find anything else. So I'll try and explain why that is. And I'll go through the previous soft X-ray studies of coproxyselenate, as well as our work on how to image and manipulate skyrmion domains. I'll try and explain how we can determine directly the topological winding number of skyrmions, and then give you some unpublished results on soft X-ray resonant polarization analysis, where we combined soft X-ray resonant diffraction and utilize the polarization properties of both the incoming and the scattered beams. And then finally I'll discuss the prospects for doing soft X-ray resonant small angle scattering as a generally applicable technique for the future. Okay. X-rays in general and X-ray diffraction, back scattering from crystals is not sensitive to magnetism. There is, however, a photon-electron spin interaction, but it's tiny. It's really, really weak. And in some amazing experiments back in the 1970s on antiferromagnetism with nickel oxide, Bergevin and Brunel, using rotating anode X-ray source, managed to actually see a magnetic diffraction peak coming from the antiferromagnetic structure, but it was very, very weak. And the scattering cross-section was estimated at 4 × 10⁻⁸ that charge scattering. So you've got to work really, really hard to see magnetic X-ray diffraction. It's non-resonant. You can have any X-ray wavelength you want, and you'll see charge scattering. It's just 100 million times harder to do than charge scattering. I wouldn't recommend it to anyone in this room. But of course, with the advent of synchrotron radiation sources, we've got tunable X-ray sources. And one of the effects that was first noted by Boone Gibbs in doing scattering of holmium was that you got an extreme sensitivity to the magnetism by tuning into absorption edges. So this shows the integrated intensity on a sample of uranium arsenide sitting on a peak and scanning through as a function of energy between 3.4 and 5 keV. And in uranium arsenide, you can access the M absorption edges, and you can see that the scattering is increasing here by 4 orders of magnitude, maybe even 5 orders of magnitude down there. And the different absorption edges have different resonant enhancements. And Marty Bloom and others managed to work out what the structure factor of resonant magnetic X-ray diffraction was, and it has a number of non-resonant terms, but also wavelength dependence, and it depends upon the scattering factors which go close to an absorption edge, where you get both real and imaginary terms coming in. So what's happening in an absorption edge is generally that you're promoting an electron from one core level up into some unfilled states. And that, of course, is an absorption, so we're absorbing an X-ray that's coming in, it's using this to jump an electron into an unfilled state. But this process happens so quickly that it then drops back down again, re-emitting another X-ray of exactly the same energy, so this is an elastic process. And it's a virtual transition because this happens extremely fast. In fact, it's instantaneous, you can't really notice. So this is a virtual excitation of an inner shell electron into an empty valence state. And what that gives you is sensitivity to the degeneracy of valence electron states up here. There are a number of different transitions, and the terminology is there are E1 is the term used for electric dipole transitions, in which this change is an L number of plus and minus 1. And there are also quadrupole transitions with an L change of 2. So, for example, here at the L3 edge, which is E1 would correspond to a 2p to a 5d, or 2p to a 4f, depending on whether it was a dipole or a quadrupole. And this is used quite a lot in particularly heavier elements like lanthanides and actinides, because as you saw in the uranium arsenide, you can get quite large resonant enhancements of the magnetic scattering. As I said, the sensitivity and the magnetic enhancement of the scattering depends upon which edge you're looking at. And these were the M4 and 5 that I showed before, where the resonant amplitude is anywhere between 100 and 300-fold. And remember that the scattering that you get out, the intensity is going to go as the amplitude squared. So suddenly you're up to tens of thousands or even hundreds of thousands, simply by exploiting these transitions, and these happen in around the 1 kV type region of the electromagnetic spectrum. When we come on to looking at B20 compounds like MNSI, FGE, carboxyselenate, then the magnetism is in the 3D shell, and the K absorption edge, which is at a convenient energy. Unfortunately, there are two transitions. There's the E1, the dipole moment, which is a transition from the 1s core electron up into the empty 4d states, manages to completely avoid the 3D shell, and therefore has very little sensitivity to the magnetism in the 3D shell, and the resonant enhancement of the magnetic scattering is extremely small. And even the E2 is similar, which is a 1s to 3D. This is the absorption edge of choice. It's to use the L absorption edges, which are from 2p to 3D, and again you get an enormous enhancement in the magnetic scattering. The problem is they're very long wavelength. So we're talking 10 to 30 angstrom type wavelengths, or less than 1 kilo electron volt. And of course, these X-rays, soft X-rays, don't travel through air. They won't get through your sample. On synchrotron, they won't even get through the beryllium window. So you tend to have to build a diffractometer and put it in a large vacuum vessel which is attached to the synchrotron without any windows. But then when you do all of that, you can see magnetic reflections. I mean, the first example of soft X-ray resonant magnetic diffraction, we looked at the antiferromagnetic arrangements in a bilayer manganite. We of course had no idea that this thing shows by Skyrmions. And here we've got a whole load of spins in this plane that are antiferromagnetic, the spins up in this plane, and this unit cell is very, very large, like 20 angstroms, and that allowed us then to tune into the manganese L3 edge, and when a single crystal was aligned on the 001, we were able to see resonant enhancement. So we're going up here to 2 million counts per second on the 001, which is a magnetic peak only. So if you look at this in the laboratory with pop count or something, you won't see a peak. There's nothing there. The 002 is the first charge peak. And yet, using the tunable nature of synchrotron radiation, we can tune in to the L3 edge, and indeed the 001, this magnetic peak, is actually much stronger than the charge scattering in this material. But there's a big problem. The problem is that the very soft energy of very long wavelengths means that we have a very, very restricted wave vector range. In most samples, the eval sphere doesn't contain a single gravity. So you're never going to use this for structure solution or magnetic structure solution, which tends to use hundreds of thousands or tens of thousands of reflections. You're lucky if you can get to one. But if you choose the system correctly with a long enough wavelength unit cell, you're very, very sensitive to magnetism. Okay, let me introduce you to copper oxysulfonate. For those of you who don't know about it, it's got exactly the same P213 crystal structure as the other B20 materials, but it's got more complicated crystal structure. There are, the copper is copper 2+, and there are 2 different sites depending on the oxygen environments in this material. And of course, it contains skyrmions at low temperatures, close to 60 Kelvin. And in one of the first studies, Shinjiro here was able to show Lorentz TM data showing us lots of skyrmions. The phase diagram is very similar to almost every other B20 material, so it's paramagnetic at high temperatures. And there's a very, very small A phase in the bulk crystal structure contained within the single Q-domain helical phase. And the ground state at all temperatures is also helical, but with multiple Q-domains. And here's the very small A phase. It only exists over about 1.5 Kelvin, but of course can be extended dramatically by making the material in thin films. And small angle neutron scattering has also shown this hexagonal arrangement of skyrmions existing within that wave phase. So this was the first example of a soft X-ray resonant magnetic diffraction, and this was done back in 2014 by LANL et al. And they tuned to the copper L edge, which is just under 1 kV. And copper oxysulfonate is in this exalted position because there is a Bragg peak available. The lattice parameter is large enough in this material. It's nearly 9 angstroms. And that means that you can get to the 100 even at this long wavelength. In fact, the 100 is a two-feature angle of about 90 degrees. And here's the 100 Bragg peak. And they observed 5 out of 6 in that picture, 6 satellites surrounding the 100. And the wave vector from the 100 to each of these satellites is about 100 reciprocal lattice unit, giving an indication of the size of the skyrmions and the spacing between the skyrmions. in the triangular lattice. And what they also noticed that these satellites were split. They were split both in angle, they were also split in energy, with them resonating at slightly different energies close to the copper 3 edge. And knowing that there were 2 copper sites in this material, they therefore suggested that these 2 resonances were because of the 2 different copper environments, and came up with a complicated explanation involving a moire pattern, which doesn't seem to make much sense in diffraction, which looks slightly different. Okay, so we've attempted doing resonant X-ray diffraction at the I-10 beamline at Diamond, and we built a soft X-ray diffractometer called Razor, which is built on a soft X-ray undulator, and the soft X-rays come through here. The sample is all under a vacuum, and we can have a magnetic field, and we can collect the scattering of this 2-feet triangle close to 90 degrees on CCD. The undulator provides horizontal linearly polarized X-rays. In fact, you can change the linear polarization. And as Bob introduced, we can even do circular polarized X-rays. Initially, we started with a beam size of 100 microns. And of course, we're doing elastic single crystal diffraction, so no change in energy using the CCD, and typically the exposure time on CCD was about 2 milliseconds per image. And what you see when you look around the 100, well, the first time you cool it down, you often find a mess. A whole ring of satellites around the 100, and this here is just a streak formed by the overexposing the CCD and blinding it momentarily. And we found, just like in the study by Wagner, that the satellites were indeed resonant. That is, they increased in intensity very close to that L3 absorption edge and indeed the L2 absorption edge. But we didn't have a nice, simple pattern, a 6-fold pattern. You can get 6-fold patterns. Here we would temperature scan, and we would change the magnetic field. Here now the 6 satellites surrounding the 100 brag peak. And so the natural explanation now for why we're seeing one satellite here, and occasionally, as in the previous slides, seeing lots and lots of satellites, is the domain structure. And here are some simulations. If the Skyrmion lattice is uniform throughout, it's effectively a single crystal or single plane. With the triangular lattice, you would, of course, get just this hexagonal pattern of satellites. Whereas if you have multi-domains, here we've got 3, this is a simulation, then you would get 3 spots around each. Presumably, LANL just happened to have 2 in theirs. And here are the 6-fold satellites surrounding the 100 brag peak. And we found these were all singlets in energy as well as in angle. And we could get 1 or 2 or 3 satellites, depending on the number of domains we had. And we were able to map out the phase diagram of the Skyrmion phase, which agreed with other studies. So you can image the Skyrmion domains. You can also manipulate them by actually changing the angle of the applied magnetic field to the sample. And so here, if there's our hexagon, I'm defining this angle psi, then if that's 0, then you tend to get a nice uniform Skyrmion domain. And if you twist it further out, you begin to break the sample up at 50 degrees, you get a large number of different domains. And if you go to too higher angle, it just goes effectively polycrystalline, and breaking them up into hundreds of different domains. One of the advantages, though, is we've got enough intensity that we can go down in size to only a few microns, and so therefore we can map out each of these domains separately, because we've got sufficient intensity coming from the Okay, so that's elastic diffraction. I just thought I would show you some work that Sheila Zhang, who's our postdoc at Oxford, working with Torsten Hedgedal, did on how to determine the topological winding number directly. Obviously, these things can be calculated and counted, but this is a nice way of being able to measure them experimentally. So here we're just showing a classical spin with n equals 2, and we're showing it in both order parameter space and in physical space where you have to go around twice. These will be the equivalent diagrams for n equals 1, n equals 3. And the experiment is rather simple. You come in with an incident beam onto your sample here, scattering at a certain angle, and then you have a equal angle that's scattering off, so this would be the 2 theta angle. We apply a magnetic field that is normal to that surface. And we define an azimuthal angle around which we can rotate the sample. And normally that would have no effect in normal Bragg diffraction. It doesn't matter that way. All that matters is the theta angle and the 2 theta angle. So here are some numerical results. Here I'm showing spin configurations for n equals 1, 2, 3, and 5 topological winding numbers. And these show, as in Don's talk, a circular dichroism. And this shows the circular dichroism cross-section as a function of this azimuthal angle, which is, I think, exactly what you did. And these then show, if you come in with polarized X-rays, circularly polarized X-rays, these show how the polarization changes as a function of both rotating the polarization angle beta, which is along here from 0 to 180 degrees, but also the azimuth angle of the sample as you rotate that around. And you can see that the number of peaks are integer and related to the topological winding number. Of course, they're all calculations. If I show you the experiment, here are our 6 satellites surrounding the 100 Bragg peak. And as we rotate the sample around, then these satellites also rotate around. And if you then measure the circular dichroism, so we measure circular left and then circular right, and get the circular dichroism, 0 would be that there'd be no dichroisms that's going from positive to negative. Then you see that you get this sinusoidal variation of the circular dichroism. And here is the experimentally measured map of the circular dichroism as a function of both the polarization angle and the azimuth angle. And that allows you to therefore show directly that the topological winding number of the Skyrmions is 1, which is not a surprise. But it does give you a way of distinguishing from Bloch and LANL and even anti-Skyrmions. So this would be the spin configuration of the LANL, n equals 1, circular dichroism. And this would show that an anti-Skyrmion with n equals -1, as you can see, although these look rather similar, these are tilted at a slightly different angle, which would allow you to calculate the topological and distinguish the topological numbers. Okay, I'm going to finish off by just showing you what more you can do with resonant soft X-ray diffraction, but this uses not the circular dichroism of the beam, but the linear polarization. So here we would come in with a linearly polarized X-ray beam, so this would be, say, horizontally polarized. And it interacts with the sample, and there'd be a scattering angle theta, and it would diffract off our horizontal sample here at angle 2 theta, and we could then analyze the scattered polarization of the beam by using an analyzer crystal. Rather than placing the detector just over here and counting, we could actually rotate this analyzer crystal in order and then detect the X-rays that are given off, so that we know both the polarization of the incoming beam and the polarization of the scattering beam. And that means we can determine the origin of any scattering So the scattering matrices are different for charge scattering from magnetic scattering and even higher order magnetic scattering. And we can calculate all of these using what's called full polarization analysis. I'm going to show the results of this full polarization analysis in terms of these Stokes parameters, P1 and P2. This is a terminology used in optics quite a lot, but it transforms directly into the X-ray region as well. And so here we show different types of scattering matrices and how the polarization, both P1 terms and P2 terms, would vary, allowing you to see both charge scattering at the top there, but also magnetic scattering and even collinear magnetic scattering structures down here. Okay, first surprise. In spite of everything I've told you, the 100 Bragg peak is not a Bragg peak. I'll say that again. The 100 Bragg peak is not a Bragg peak. Actually, if you look in the diffraction pattern, at any wavelength you most normal wavelengths, you won't find a 100 Bragg peak. And clearly, when I showed you the earlier results, there's a huge intensity here. But it's structurally clean. It has, because of the crystal structure, has an intensity of 0. It only has intensity when you go close to an absorption edge. And that's because of the scattering going complex and having real and imaginary terms. But all other wavelengths, there is no Bragg peak there. And so when we measured the intensity of the 100 Bragg peak, you find that at most energies or wavelengths, the scattering is 0. It just comes up enormously at the L3 and also at the L2. And indeed, the satellites also have 0 intensity at any normal wavelengths. There's another weird thing about the 100. Unlike any normal Bragg peak, it causes a polarization change. In fact, it rotates the polarization of the beam by 90 degrees. So if you come in with linearly polarized X-ray radiation, it will actually transform that. The scattered beam will be vertically polarized. And so here we show the Stokes parameters P1 and P2, showing this change of polarization by 90 degrees. And that's known as anisotropy of the tensor of X-ray susceptibility, which is a complicated term meaning this is a weird Bragg peak that is not really a Bragg peak but comes from the scattering terms of forbidden reflections. When we went and measured the helical satellites, this was what we were expecting in solid, and the points are actually what we measured. And therefore, it seems to suggest that the helical satellites are not helical, which was a bit of a shock. It turns out that you can fit the helical satellites and you can get a good agreement between the experiment and the data, but don't fit them as helices, instead fit them as very long wavelength spin density waves. And not only the helical ones, the conical and even Skyrmion satellites in this experiment appear to be long wavelength spin density waves. Before you start to think that I'm claiming that Skyrmions don't exist, I'm not. What I'm saying is when you look at the polarization dependence of the satellites around the non-100 Bragg peak, we're measuring a wave vector, which is not the wave vector of the Skyrmions, or the helices, or the cones. Actually, their wave vector is down close around the origin. That's the primary wave vector of these things, and we need to access them, and we can't. So finally, I'll just finish with how do we access the lattice reflections in things other than copper oxyselenate. Instead of working around the 100 symmetry forbidden Bragg peak, actually what we want to see is the Skyrmions directly. And they are found at very, very low angles around the main beam. And hence, we need to use small angle electroscattering. And it was pointed out by Eric that he first suggested small angle resonant magnetic diffraction back in 2001. And we followed the work from Rickham. And here, this is the technique. You have a slice of your crystal, you have a 3 micron beam coming in, and you measure the satellites at very, very low angle. This is the coherent scattering coming from our 3 micron beam. And that allows you to directly access not just the helices, but the Skyrmion reflections. So here we've got 6, these ones we didn't see, we don't know why. These 4 we did with a scattering angle between 60 degrees, and this shows the transition up into the contour. So I think this is the technique for the future. We should all be doing resonant soft X-ray scattering. It's a technique that is similar to neutron small angle scattering, but we've got much higher intensities, much greater sensitivity to magnetism, and we can play tricks with circular dichroism and polarization. So with that, I'll finish. Thank you.
Concerning the spin density wave, is it what is the period of the spin density wave? Is it the same as the chemical, or is it rather conventional?
Right. So we're looking. It is the origin in reciprocal space, and the little Skyrmion satellites or helical satellites would be close to the origin. Instead, we're looking right up around the 100 bragg peak with really long wavelength X-rays. And the satellites, whether be them helical or conical or Skyrmion, are very close to the 100. And that means our wave vector is something like 0.010. So when we come to model that, we're not getting information about the scattering actually in the plane with the Skyrmions and cones. We're looking at something that's like 100. And that's the reason you get these very, very, what appear to be very, very long spin density waves. Because you're looking directly up the 100 in that direction. You're getting only the components in that direction, and you're not seeing the components actually in the plane. There is a way, of course, we need to do resonant small angle scattering on those satellites and do the polarization analysis. The problem is you're very close to the main beam, lots of intensity from the main beam, etc. So you have to be careful.
Topological chart of a Skyrmion has the notion of the scalar spin chirality.
Yes.
We know that it breaks the time inversion symmetry, and therefore it produces a topological orbital moment, or topological orbital moment density. Do you see a chance that with the dichroism part, with the X-ray scattering in this soft X-ray regime, to map out actually a topological charge density? So basically, you have to measure the scattering in the so to say, the orbital moment response. I think you know what you mean.
Right, so you can, using soft X-ray scattering, you can determine orbital ordering and magnetic ordering and charge ordering, and you can distinguish all of those from their different polarization properties and their different dichroisms.
I mean, the effect is small.
Yes.
What do you think is your sensitivity of orbital moment versus spin moment?
If you go onto the absorption edge, close to the absorption edge, actually, as you go through that absorption edge, the sensitivity to orbital and spin will change.
Okay.
So I think by doing those measurements at a number of very close, so generally the greater sensitivity to magnetism will be almost on the top of that resonance. The orbital ordering, you tend to get greater sensitivity if you back off a few fractions of an EV. It can vary from one element to another, but manganese, iron, cobalt, they're all roughly the same. So, yes, I think that is possible in the future.
So I have to kind of follow up on what Mark was asking, because I still don't understand. I mean, I see you can, see the satellites that are perpendicular to your 100. But so you're talking about is the density bay that appears to be in that direction. So what is that? Because you're saying that basically those Skyrmion tubes are modulated?
No. I think it's simply that we're measuring the X-ray scattering in a wave vector direction that way. And therefore, we tend only to see the components that are in that direction, and therefore what we measure is something that looks to us like a spin density wave going up there. It's not. The actual magnetic objects, Skyrmions, helixes, the conicals are in this plane.
Right.
It's because we're not using a primary reflection. We're using satellites around a forbidden drag peak. And therefore, we're looking in the wrong direction.
So then what are we learning from this piece?
Nothing. Well, sorry, we could image. We were able to image the lattices. You can get the size, you can get the wave vector, and therefore the triangular lattice, but that's been known from the Lorentz TM and from neutron small angle scattering. You're not learning that much more, unfortunately. I think you need to go down to the primary Skyrmion reflections, which are very, very close. Have wave vectors of 100th OO and 100th
The biggest confusion that is in my mind is that, so you're saying it's SDW, right, which can interpret you as linear. So is this result that you're getting is consistent with just looking at particular things and constantly actually beats those consistent to those 3D Skyrmion tube type structure, or?
I think that's pushing the analysis too far. Right? I think what we are seeing is the effects along that direction. And of course, if you have 3 of those directions, it would produce something like a Skyrmion, but actually we're not really looking at Skyrmion.
Sure, but at least it seems like there's still something to understand, right?
So whether I think I might understand what's happening. So essentially, if you look just up, there's no modulation because the Skyrmions are standing. But he's saying he's looking up, but there's slightly bit tilted. So you're always going over, a little bit, and that is a modulation because you're going from spins that are like this in the center to slightly rotated. So you're looking sort of in a diagonal way along the Skyrmion tubes. So that way they seem to.
So that you understand why there should be beams actually, why it's not just some sort of non-resonant feature. Because so it seems like there's a beam which is very low by some case base, right? So there got to be something there.
We don't know, but it's
There is that modulation base.
So do we know what so is it known there is modulation? Or?
No. I mean, basically what happens is that he looks around the 100, and then there's satellites of the 100 that are sort of perpendicular, right? And the problem is he doesn't have the resolution to really distinguish those. So they all look like 100. They're 100 plus a little something. So then you go, slightly diagonal, and in this case there is a modulation.
So eventually be consistent with what we think we know from the.
Yeah.
Yes,
So
It is.
It is a consistency check, but the best way would be to actually go to the reflections down here in the plane and then measure direction of the Skyrmion. So you could measure the magnetic anodes optically of the Skyrmion there directly.
Right. Okay, any other questions? Now we'll take a break and come back. 20 minutes. Thank you.
So basically, let's say this is a used gun.